Mechanics students, now it's time to take all your skills on the method of integration to solve for beam bending deflections and to try it yourself in this example problem. So I think you have all the tools to get started to solve this problem. So go ahead and give it a try. If you need a little bit of music inspiration, check out this. Oh, mechanics students, how am I supposed to know? If you have questions right now, oh mechanics students, I hope you enjoy these videos and write me any doubts now. I must confess, it can be tedious to calculate deflection in beams. Yes, it will be harder than it seems. But just try it right here and keep track of your signs when you integrate it one more time. Well, I hope you're thoroughly inspired by our 90s theme day to solve for deflections and beams. We see in this problem we have a distributed load and a point moment applied to a simply supported span, and we're asked to calculate the deflection at C. We could come up with the combined moment equation for this, but I think it's easier if we separate the two load effects. So I separated it into case 1, which is the distributed load, and case 2, which is the point moment. So just like all the other examples, let's go ahead and start by drawing the shear and moment diagrams for these two cases. So pause the video here while you do that, and then I'll get back to you. Alright, so hopefully this is what you found. One of the most common problems I see is that people believe in case 2 that there's no shear. However, if we just apply our equations of equilibrium, you will see, just using static equilibrium, that we definitely get reactions at both A and B. They're equal and opposite. And then we have a shear and moment diagram that we can draw using those reactions. So in this problem, we're asked to solve for the total deflection at C. And using superposition, this will be the total deflection at C due to case 1 and case 2. We can apply superposition anytime we have elastic structures, which is one of the assumptions we made in our bending deflection equations. So what is the deflection at C for case 1? Well, we solved this in example problem 1. We found that it was minus 5 omega L to the 4th over 384 EI. If you have any questions on how this was derived, I'd say go back 2 videos and check out example 1 again, and you'll see how we came to this formula. Now, what is the deflection in case 2? Well, that's a little harder to see, but we do know that our moment diagram can be a linear equation, and it has a slope of m0 over L times x. If we take x to be at the left-hand side, x equals 0 is at point A. You can now use this equation to start your method of integration to solve for the bending deflection. So if you were a little unsure where to get started, go ahead and use this moment equation and go ahead and try the method of integration to see if you can do it. Now, like we begin with all of our bending deflection problems, we identify boundary conditions. So go ahead and identify those boundary conditions for case 2 and then try the method of integration. When you're ready, start the video back up here to get a full explanation. Alright, so for the simply supported case, I'll use the 2 deflection boundary conditions. So we say y of 0 equals 0. That means the deflection at A is equal to 0. And the other boundary condition is y of L equals 0, which means the deflection at B equals 0. For this particular loading, I have difficulty coming up with any slope conditions because I don't really know the slope of the beam at any point, so I wouldn't come up with any slope conditions. Now, since I'm starting at the equation for the moment that I derived, I really only need 2 boundary conditions to solve this problem. So I'm going to use this moment equation, m0 over L times x, and that is how I'll start my calculations for the method of integration. I'll start from the second differential equation relationship, so namely EI y double prime equals m of x. Next step is to integrate. So I integrate both sides. That will leave me with EIY prime on the left-hand side, and then M0 x squared over 2L on the right-hand side, plus my constant of integration C1. Again, I don't have any slope conditions, so I can't solve for this constant yet. So I'm going to keep the constant around. Integrating both gives us EIY equals M0 x cubed over 6L plus C1x plus C2. Now I have two deflection boundary conditions, so I'll be able to solve for C1 and C2 in this case. So starting with my first deflection condition, y of 0 equals 0. So plugging in y of 0, I get 1 over EI times M0 times 0 cubed over 6L plus C1 times 0 plus C2. All that has to equal 0. So everything goes away except for C2. So that means C2 is going to equal 0. My other boundary condition is y of L equals 0. So this is the deflection at B. I plug in everything with x equal to L, so that gives me M0 L cubed over 6L plus C1 times L plus C2, but C2 is 0, so that'll go away. Now I need to solve this for C1, so I get M0 L squared over 6 equals negative C1L, and then I can divide both sides by L, so I see that C1 is negative M0 L over 6. All right, once I have my constant solved, I can then find the final equation for the deflection, y of x. Y of x will equal 1 over EI times M0 x cubed over 6L minus M0 L over 6 times x. And this is the equation for the deflection of the beam in case 2. Now, if I wanted to get a combined version, I could take the y of x for case 1, and I could take y of x for case 2, and I could just add them together, and that would give me some polynomial combination for the total deflection of the beam given in the problem. But I'm focused on figuring out what the deflection at C is in the middle. And so for case 2, if I just look at the middle, well, that's going to be y of L over 2. So everywhere I see x, I'm going to plug in L over 2, making sure that that L of 2 makes it into the parentheses, so that when I cube it, that 2 in the denominator also gets cubed. Working through our algebra, we end up with 1 over EI times M0 L cubed over 48L minus M0 L squared over 12. So my L cubed and L in my first term will cancel, so that will leave me with M0 L squared. 1/48 M0 L squared minus 1/12, so 1/48 minus 1/12 is going to give us negative 3 M0 L squared over 48. And don't forget the EI from outside the brackets. So now we have a formula for the deflection at midspan for case 2. It's probably prudent to go ahead and plug in our values for each of these, making sure that we keep our units consistent. So I'm going to put everything in kips and inches. So I'm going to convert M0 from kip feet into kip inches. I'm going to keep L in units of inches. Divide by 48 times E times I. So checking back, E is 29,000 KSI, and I is 82.8 inches to the fourth. All right, so plugging that into our calculator, we can determine that the deflection at midspan for case 2 is negative 0.1594 0.00 inches. Again, the negative sign meaning that it's a deflection downward. So returning back to our problem, we'll go ahead and make a note for what the deflection for case 2 was calculated to be. Now we haven't quite found the deflection for case 1 yet, but we have the general formula, so we just have to plug in our variables and solve for the deflection at C for case 1. So we have -5, omega was 0.5 kips per feet. We need to convert that to inches, so I'll multiply by 1 foot over 12 inches. The length is still the length of the entire beam, which is 20 feet or 240 inches. Raise that to the 4th power, divided by 384 times 29,000 KSI times 82.8 inches to the 4th. So running those numbers through our calculator, we get the deflection due to case 1 at point C was minus 0.749625 inches. Alright, since we were using superposition, we now can calculate the total deflection at the middle. Unsurprisingly, when we add these two together, we get negative 0.9090 inches. Come on, you didn't expect me to ruin 90s day. So hopefully you had a feeling that that was the deflection going in. So hopefully you made it through this problem, hopefully with not too many bumps or bruises. Hope you had a great time. I had a great time with you, and I'll see you in the next future videos.